So I have to cover up nitrogen sulfur. The first part of nitrogen they want you to remember, and we've done this earlier in, I guess earlier years also, is that it's an unreactive molecule. The nitrogen gas is N2. There it's unreactive because it has the strongest triple bond. In fact, the strongest bond we've ever seen so far. This fellow is a good 900 plus kilojoules per mole. So this is a very, very strong bond, which means is unbreakable almost, and it's a non-polar bond, which makes both of these reasons makes nitrogen unreactive. That's the idea. That's simply it. Nitrogen gas. The only times it actually reacts is during, uh, you know, thunderstorms and those lightning with high voltages and the very very high temperatures in the car engine. Those places are that have high enough energy to break this bond. Else, we consider nitrogen to be an unreactive gas. Wherever we need to use an unreactive gas in the world, we actually literally just use nitrogen. It can be thought of as unreactive almost as helium is. Yeah, so that's it to do with reactivity of nitrogen. Let's talk about its basicity now. Ammonias, basically. Now, ammonia is the more popular compound of nitrogen that we use. It is considered a Bronsted base. Now, what is a Bronsted base? It is a proton acceptor. Now, how do I know? Literally, this is what it does. Ammonia takes in NH plus to become NH4 plus. It literally becomes NH4 plus. It's a proton acceptor. It can react with HCl gas even, and the NH3 becomes NH4 plus, and Cl minus is left behind. Here in both these cases, ammonia is acting as a proton acceptor. Um in water also, and we've seen this, ammonia can behave like that. So it's a weak base in the water. So when you mix it with water, it forms a reversible reaction, and some of the ammonia becomes NH4 plus and leaving behind OH ions. So ammonia is the base basically. It's a Bronsted base. Base, base, base. Yeah. Which actually makes what? Ammonium, which is the conjugate acid of ammonia. Yeah. That's important. Why? Because ammonium, sorry, can become ammonia again. That's the thing. Yeah. Because if ammonium, think about this, and I'll take ammonium now. So ammonium is an acid. Now, when I add hydroxide ions to ammonium, sorry, they form ammonia. And basically, you can do this. You can literally add hydroxide ions to ammonium ions, they make ammonia. This is a test for ammonium ions in the lab also. Add NaOH and warm, you get ammonia gas. So here, the conjugate acid of ammonia, which is ammonium, will liberate ammonia back. So ammonia base reacts with acids or protons to become acids, and the acid can react with the base to make the conjugate base all over again. This is, yeah, stuff that I'm sure we've already seen in O levels also. The fact that ammonia can become ammonium. NH3, 8 plus HCl becomes NH4. So yeah. The next thing, just to get over, is the oxides of nitrogen. Now, if you remember, we discussed oxides of nitrogen, where we discussed pollution also in alkanes. Because the two places where you're going to find oxides of nitrogen, which are NO or NO2, are during lightning strikes and in the high temperatures of an internal combustion engine. Internal combustion engines are really the gas engines, the gasoline or petrol engines of cars. And internal combustion engines have very high temperatures where air passes through, and high temperatures where the air can break down the nitrogen to form oxides of nitrogen. And then these oxides of nitrogen can cause pollution of different levels. One is they are catalysts, and the catalytic activity, in fact, results in the oxidation of SO2. So, like SO2 can react with NO2 to form SO3 and NO. And you might say, why is SO3 bad? Because SO3 can react with water and become H2SO4. On the other hand, the NO finds a little bit more air and becomes NO2. And if you think that you don't have NO2 but you have NO, then the NO can easily become NO2 and then cause this reaction. This is seen before already in, again, pollution for the with alkanes. The idea was that oxides of nitrogen can oxidize sulfur dioxide to sulfur trioxide, which causes acid rain. And acid rain does what, by the way? This can cause acid rain, makes acid rain. And acid rain is bad for us because it can destroy buildings, because it is acidic and buildings are alkaline. It can kill aquatic life in the rivers and the seas. It can cause irritation on the skin, reaction, burning eyes, multiple things. Acid is not good for us. Yeah, I mean, as a human interaction device. On top of that, the NOs can also cause photochemical smog, and that's something that you have to also know. They form photochemical smog. That's what's happening most days these days, because what's happening is the NO gas with unburnt hydrocarbons, sometimes from the car engine, because sometimes the engines don't burn all the hydrocarbon going through them. Okay, uh, then they make what do you call it? Photochemical smog. This is what it makes your smog in most cities now. This is basically pollution at the ground level, air pollution at the ground level, and you'll find this in mostly cities, not forests, not villages, because cities have a higher concentration of motor vehicles, right? So nitrogen oxides and unburned. So nitrogen oxides could be both NO or NO2. So nitrogen oxides could be NO or NO2, react with unburned hydrocarbons. Okay, so they form basically what they form sometimes these molecules called PAN, peroxylate, basically nitrates, which you don't need to know the formula for. They're the ones that cause photochemical smogs, basically. Okay. So let me repeat. Yeah, unburned hydrocarbons from vehicles with oxides of nitrogen react in sunlight. You generally have to have some sunlight to make smog, which is this chemical PAN. Just now, why is this bad? It's both. Uh, it irritates the eyes. Irritates the eyes. Irritant. It's an irritant and a toxin. It's toxic. Smog is. Yeah, and that's basically what you have to know about this stuff. Okay, it can cause breathing difficulties, stuff like that, right? So, yeah.